All right, so in this video kind of shows you what I was showing you, but it's a little bit, it might be a little bit, it might make a little bit more energy here. Energy, a little bit more sense here. Energy seems to be the key word of the day. So here are the atomic orbitals. You have an s orbital. You only have one orbital. All right, and then in the 2, in n equal to 2, you've got an s orbital plus you have 3 different p orbitals. In n equal to 3, you've got s, you've got 3 different p's, and you got 5 d's. And then the 4, you've got an s, you've got 3 p's, you got 5 d's, and you got 7 f's. Okay, and you remember I talked about the electrons at 2 maximum and n equal to 1? Well, that's because you can do 1 electron up in an orbital and 1 electron down for a maximum of 2. For this one, you have 2, 4, 6, 8. That's where your 8 comes from. This one, 2, 4, 6, 8, 10, 12, 14, 16, 18. All right, do you remember how many I said here? All right, I believe I said 32. That's because it's 18 for this and then another 14 for this, which is 32. Okay, that's where these numbers are coming from, is based off of how many different orbitals we have. Okay, now in reality, the orbitals aren't that nicely stacked up. They actually are kind of staggered in a way. The important thing I want you to notice, which we will talk about right now, don't memorize this, but you notice your 3Ds are higher in energy than your 4S. Okay, don't get bogged down in thinking, well, if this is a 3, this has to be lower energy than 4. They just chose numbers. Don't think of numbers in the exact order. Okay, it works mostly. So here's 1, and here's my 2s, here's my 3s, but then the 4s is actually lower in energy than my 3ds. And I'll kind of show you how this works on the periodic table. It's going to make a lot more sense. Okay, but I just want to make sure that you realize it's not perfect. It's not exactly how you think it is. Notice the 5 is in between a 4p and a 4d. Okay. So here's kind of a practice problem. Consider each of the following sub-level designations. Determine if each is legitimate. That means if I have shell 1, okay, remember shell n equal to 1, what orbitals, so here's shell, not orbitals, what subshells are allowed in shell 1? Well, remember it was only the s orbital. All right, remember n equal to 2, I can get an s and a p. And n equal to 3, I can get an s, a p, and a d. And n equal to 4, shell 4, S, P, D, F. So in the first shell, I can't have a P. I only have an S. So that won't work. Shell 2, can I have an S? Yes, every shell you can have an S. So that is correct. Shell 3, can I have an F? No, there's no F there, so that does not exist. And in shell 4, can you have a P? Yes, you can. So that does exist. All right, this is a classic problem, just to kind of let you know, will this work? All right. So here's the answer. We kind of did it. You can kind of go on your own and see that. Let's now start talking about electron configurations and how you describe this. Electron configurations, I kind of talk about it as a zip code for the electrons in an atom. All right, they talk about it by showing you the specific arrangement of electrons. It kind of shows you what energy levels and what sub-energy levels all the electrons are in. Okay. So you'll kind of see this. It's like a 1s1 or a 2p4, all right? And they always show a whole number in front, and then a letter, and then a superscript number, okay? This number, our first number, is our shell number. What shell is the electron in? The s, obviously, is then followed by our subshell. What subshell is it in? And then this number up here, our superscript, is the number of electrons in the subshell. Okay, let me see, and then the orbital diagrams, we'll talk about that later. So let's just kind of start doing this. So imagine here's my periodic table. Okay, let me kind of do this periodic table again. And I started doing this earlier without you realizing it, unless you did realize it because you've learned this before. Okay, so 1, 2, 3, 4. I think 1, 2, 3, 4, 5, 6. Perfect. All right, and then we should have one here. Sorry for the crude drawing. Okay, so here's hydrogen. Here's helium. Okay. Now I'm going to show you on the periodic table how this works. Okay. 1, 2, 3, 4, 5, 6. And there's another one right there. So if you count how many periods there are, 1, 2, 3, 4, 5, 6, 7. There are 7 periods on the periodic table. Okay. Notice on the previous page, it only went up to 7 shells. That's because these are my shells. Each of these is a shell. So here's shell 1. Shell 1 n equal to 1. Remember, I only have an S, and I can only hold a maximum of 2 electrons. Well, that's why I have only 2 atoms on period 1, because that's shell 1. Okay, so remember Bohr's model. You can kind of use Bohr's model, but even though it doesn't really exist. Okay, so remember here was n equal to 1. Maximum of 2 electrons in here. I can hold 0 electrons, I can hold 1 electron or 2 electrons, no more. Hydrogen has 1 electron. Okay, so where is that electron found? Well, it's found in shell equal to 1. So it's found in shell 1. It's found in an s orbital, because remember, all you have are s orbitals, and subshell, s subshell, and there's only 1 electron found in that s subshell. So the electron configuration is 1s1. This tells you the shell it's in, this tells you the subshell it's in, and this tells you how many electrons there are. So it's telling you the specific arrangement of the electron. Okay, so that's the electron configuration for hydrogen. For helium, there are 2 electrons. So where are the 2 electrons? Remember, maximum of 2 into this n equal to 1. So helium, it's in shell 1, it's still in the s subshell, and there's 2 maximum electrons. Remember, n, I can only have an s. I cannot have a p. There are no p's in 1. I can never have a 1p. 1p does not exist. Now, once we get to 3 electrons, remember, I can have an s and I can have a p. 2 electrons for the s and 6 total electrons for the p, for a total of 8. Okay, so let's go to lithium. Lithium is right down here. Okay, so lithium has 3 electrons. So first of all, where are the first 2? Well, the first 2 are in n equal to 1, and now I'm going ahead and doing my n equal to 2 right here. Okay, so hold on 1 second. All right, I was actually on pause for a while. You might not have realized it because you're on video, but I just got my cat out of the room. Okay, so shell equal to 2. We have an S and a P, 2 for the S and 2 for the and 6 for the P. So first I'm going to fill up the S subshell. So lithium, okay, lithium, 2 of them are in the shell 1, s orbital, and there's 2 electrons. The third electron now for lithium has to go into shell 2. Okay, now which subshell is it going in, the S or the P? Well, which one's lower in energy? Always go to the lowest energy first. S is always lower in energy. So the third electron is going to go into shell 2, all right, into the S orbital, and how many electrons are there? There's only 1. So if you were to count these, that will tell you the total number of electrons that lithium has, which is 3. Okay, you guys following this? Let's go to beryllium. Beryllium has 4 electrons. 2 of them are in the 1, S. So beryllium, 1s2. And now the other 2 go up into the s orbital. Now, do I put one of them in the p yet? Because what's the maximum I can hold in this s? 2 electrons. Well, I have 2 electrons. So I'm going to put all of them into the 2s. Okay? Now I can't fill the 2s anymore because it's maxed out. So if we go to boron, which is right here, boron has 5 electrons. Okay, 2 of them are in the 1s2. Okay, another 2 of them are in this 2s2. But remember, I also have a p in the n equal to 2. N equal to 2, I have a 2s. I also have a 2p. Once I've filled up my 2s, I now start filling the 2p. So this electron now is in the 2p, and there's only 1 electron in it. Okay, hopefully that makes sense. So carbon is right here. Carbon has 6 electrons. Where am I putting this last electron? Well, so this is boron. Well, I can hold a 6 maximum in the 2p. I got to fill this up before I go to shell 3. Remember, shell 3 is out here. N equal to 3 is shell 3. So I got to fill this up because 2p is low in energy than any of my 3s. So notice carbon now is going to have 2 electrons in 2p. So carbon is 1s2, 2s2, 2p2. All right. Nitrogen is going to be a 2p3. Oxygen, 2p4. Fluorine, 2p5. All right. And finally, fluorine. Did I not have enough here? So nitrogen, oxygen, that's fluorine. Sorry. This is neon, is 2p6. All right. So neon, just to do it, is 1s2, 2s2, 2p6. So I have the 2 in the n equal to 1, 2 in the 2s. The 2p, you can kind of think of it as a subshell just a little bit higher than the 2s, if you want to think of it like that. And then I can hold a total, hold a total of 6 in there. 1, 2, 3, 4, 5, 6. Okay? Now, down here is sodium. What do you think I start doing with sodium now? Well, my 2p is filled up now. Notice I'm in period 3. So now this last electron now is in the 3s1. So that would be now for sodium. Sodium is 1s2, 2s2, 2p6, 3s1. Okay, so hopefully you're kind of seeing how this is being arranged. And our periodic table is arranged like this. Now, I hope this drawing isn't too confusing. Let me actually draw it on a little bit more space here. Let's see. Yeah, actually, we'll just do it here. Okay. So, well, actually, yeah, let's just do it right here. Kind of give you a little bit more space. I don't know if this is better or not. 1, 2, 3, 4, 5, 6. Here we go. And then we have this that goes all the way across. Oh, I didn't mean to do that. So the periodic table is arranged in this specific order. Okay, I'm just doing this bigger from the previous page just so you can kind of see it. I don't know if I have all the right ones. So this is 1, this is 2, this is 3, this is 4, this is 5, this is 6, 7. These two blocks are what's called the S block. This 6 is the P block. These 10 is the D block. And then down here you have 14. This is called the F block. Okay. So notice hydrogen is a 1s1. Okay. So right here, this spot is lithium. This is a 2s1. This is a 3s1. This is a 4s1. This is a 5s1. This is a 6s1. Francium, which is right here, is going to end in 7s1. Okay? This is a 2s2. This is a 3s2. 4s2. 5s2. 6s2. 7s2. All right? So this is how the periodic table is arranged. This isn't by chance. Okay, this is exactly how the electron configurations work. This is my P block. So everything in this row is going to end in what? P1. This is going to be a 2P1. This is a 3P1. This is a 4P1, 5P1, 6P1, 7P1. These are all the P2s. 2P2, 3P2, 4P2, so forth and so on. P3s, P4s, P5s, P6s. Okay? So down here, which I believe is radon, is going to end in 7. No, I think radon is right here. Is going to be a 6p6. Okay? So this is how this works. All right? So whatever the period you're in, that's the shell, and all depending on the block. All right? So it's very simple. It's very straightforward, and you just follow along. Okay, now this becomes confusing. Right here is scandium. This is the start of the D block. Notice the D block is starting in shell 4. Okay? However, we need 3 Ds. So scandium is actually a 3D1. So your Ds are 1 less than what period you're actually in. Okay? I believe this is titanium. All right, this is a 3D2, and so forth and so on. So all the way to 3D10. Okay. I believe this is copper, Cu right there. I'm not 100% certain, but it's going to end exactly at the 3D10. So everything in here, what are these Ds? These, if you guess the 4 Ds, you're correct. These are all 4 Ds. 4D1 all the way to 4d10. And then what do I start back right here? This is the 5p's. All right. Then I have the 5d's. All right. But then I jump to the 6p's. And then here I have the 6d's. Okay. Now the F's are just like this, but remember the F's squeeze in right here. Okay, that's where the F's actually fit in, and the F's are 2 numbers less. So if this is period 6, this row up here are the 4 F's, and this is the 5 F's. So the 5 F's fit right here. The 4 F's are right here. So it goes 6 S's, then you go to the 4 F's, then you go to the 5 D's, and then you go to the 6 P's. Okay? So if you are doing the electron configuration of whatever atom, it doesn't matter what atom, I kind of already have given you kind of the answers to everything. Okay? So let's say I'm doing the electron configuration. I'm sorry, this is actually zinc right here, not copper. I said copper. That should be zinc at 3d10. Gallium. Gallium, this is getting kind of all messy. Let's actually go, I know there's a periodic table down. Let's just go back. Let's kind of erase some of this stuff in here. Actually, I'll tell you what. Do the electron configuration for gallium. Gallium is Ga. See if you can find it on the periodic table. It's atomic number 31. Okay? All right, so put this on pause, find gallium, do the electron configuration, come back, and I will give you the answer. All right, hopefully you paused, and I'm going to give you the answer right now. If you haven't paused, then pause it and do it. Okay, let me just kind of erase all this. Okay, so gallium, let's just kind of do a generic periodic table here. It's going to be pretty fast. All right, gallium, I believe, is right. So you have boron, you've got aluminum, and you got gallium right there. Okay, that's aluminum. There's gallium. Okay. So if we go on my periodic table, I know this is a little messy, but hopefully this makes sense. Okay, you basically do all the electrons on this whole entire thing starting in order. So it's going to include these electrons, the electrons all in here, the electrons all in here, and then the electrons up to gallium. Okay, so if you look on the periodic table, you're going to fill the 1s2, and then the 2s2, and then the 2p6. Then the 3s2, the 3p6, all right? Then you can go to the 4s2, all right, which is right here. These are the 4s2s. Then you're going to fill these, which are the 3d10, and then you start back up to the 4p1. So that should be the electron configuration for gallium, okay? I hope that made sense. If it doesn't, we'll do lots of problems, and you can ask me questions in class, all right? But hopefully, by now you kind of understand electron configurations and how this is going. I know there are practice problems throughout this presentation. All right, let me just kind of erase all quickly. Okay, so that's electron configuration. This slide now talks about orbital diagrams, which actually now start showing you individual electrons. So let's say carbon. Do the electron configuration for carbon. Okay, do it right now. Put this on pause and do the electron configuration. Okay, we are back. The electron configuration is 1s2, 2s2, 2p2. Okay, that's the electron configuration for carbon. Now, the orbital diagram shows you individual orbitals and electrons. Electrons can either have an upspin or a downspin, and they like to be in pairs. They like to be paired up. Okay, so the orbital diagram for this would be, remember, the S subshell only has one orbital. So you have one electron up, one electron down. That's the 2 electrons. So this is the 1s2. The 2s2 is also a single orbital, which is a box, and you have another electron up and another electron down. Okay, now I have p orbitals. There are 3 individual orbitals. Okay, so that's how you draw this. All right, and I have 2 electrons. Now there's 2 ways of doing it. I can either do 2 unpaired, or I can maybe do 1 paired and 1 unpaired, since I told you these like to be paired up. There are 2 possibilities. One of them is correct, one of them is not. This is not correct. Okay, it has been found that it's lower in energy to first fill up all your orbitals with unpaired electrons, then go back and fill them up. All right, and this is Hund's rule. I believe they talk about it in one of the later slides, but I just kind of want to give it to you now. Okay, Hund's rule says unpaired first, then paired up. So nitrogen, which would have another electron, which would be an sp3, would look like this in your p's, all unpaired. And then oxygen is 2p4. Oxygen now, you will have the 3 unpaired, plus now you have 1 paired. You go back and pair it. All right, and then fluorine would have 2 paired, and then finally neon would have them all paired. Okay, and that's kind of what they are showing you right here. They're showing you we can use orbital diagrams to write the electron configuration. It gives you more information. Notice it's giving you more information. It's showing you what electrons are paired and what electrons are not paired. Okay, so this is talking about different spins. You either have a spin up or you have a spin down. That's why they are pairs. You always have a spin up and a spin down. Okay, and this kind of tells you the rules. Electrons always occupy the lowest energy orbital. All right, an orbital can accommodate a maximum of 2 electrons. That's why it's a spin up and a spin down. Okay, that's the Pauli exclusion principle says that any 2 electrons can apply the same orbitals as long as they are opposite spins. Okay, and then Hund's rule is you first do unpaired first, then you go back and pair it. So orbitals of equal energy will each get an electron before any of them get paired up, or you put in a second electron. Okay, so here again, this is the example I already showed you. Here's lithium. Lithium's a 1s2. All right, so you have 2 here and 1 there. Here's carbon. Here's the carbon example. First unpaired, so that's Hund's rule. All right, oxygen are unpaired, and then you go back and pair it because you have a 2p4. All right. All right, now here's neon. This is an abbreviated form, okay? Let's say you're doing a very long electron configuration, okay? And what you do is you do what's called a noble gas abbreviated form, a noble gas core abbreviated form. So for example, this atom, I believe, is sodium, okay? Sodium is a 1s2, 2s2, 2p6, 3s1. Well, the previous noble gas, so you always look at the noble gas before the element. So the noble gas before sodium is neon, all right? And neon has the electron configuration of 1s2, 2s2, 2p6. That's neon. So notice this is the electron configuration for neon. So instead of writing all this out, you do an abbreviated form. You basically put the previous noble gas and then everything that is left over. So whatever's left over is a 3s1. So for practice, do the electron configuration for chlorine. Do the, no, actually, let's do bromine. Bromine. Do the electron configuration for bromine. Go now. Okay, we are back. So the abbreviated form. So bromine, the noble gas before bromine is argon. Okay, that's the noble gas. Remember, the noble gas is the group 8. Then everything after that. So after argon, we jump down to the 4 S's. So 4s2 are filled. Then we go to the 3 P's. Remember, the 3 P's are next, 3b10. Then we go back, I'm sorry, D's. That's a 3d10, not 3p, 3d10. Then we go to the P's, the 4 P's. So 4p and bromine is the 5th one, so 4p5. So you should have argon, 4s2, 3d10, 4p5. All right. Here are just some sample problems. You can do these on your own, but basically it's the same thing. It's doing electron configurations and orbital diagrams. And then, again, ask questions, write down your questions. I hope you have questions. I don't expect everyone just to get this automatically. If you do, that's great. But we need to spend some time doing problems in order to get it. And don't worry, you will get it. It's really not as hard as some people think it is. All right? All right, I'll see you in the next video.